All right, today we are going to dig into a question with an answer that might just completely flip your understanding of how things work. We're going to unravel this thing called the elasticity paradox, and we're going to find out why in the world of physics, steel is actually considered way more elastic than rubber. So let's just kick things off with a simple question.
So I'm asking you straight up, which one do you think is more elastic? A rubber band that you can stretch out like crazy, or a solid, stiff steel spoon? Just take a second. What does your gut tell you?
Okay, if you said rubber, you are not alone. I mean, that's what our everyday common sense experience tells us, right? But here is the major twist. Physics has a completely different answer. According to the science, steel is the right choice. So how on earth is that possible?
Yeah, this surprising clash between what we think we know and what's actually true in science, that's exactly what we're going to unpack right now. You see, the whole mystery, the whole paradox, it really just hangs on one single word: elasticity. Turns out the way we toss that word around every day is totally different from its real scientific meaning. So to crack this puzzle, we have to start there, with the physics definition. Let's break down the actual physics of elasticity. It all starts with a couple of really important forces. First up, we've got something called a deforming force. Now, this is pretty simple. It's any push or pull you put on an object to try and change its shape. Stretching a rubber band, squishing a stress ball, that's you applying a deforming force. Easy enough. Okay, now here's where it gets really cool. We need to talk about the restoring force. See, when you try to deform something, that object actually fights back. It creates an internal force that tries to pull or push itself right back to its original shape. That is the restoring force. When you stretch a spring, you can literally feel it pulling back on your fingers. That's it in action. And this brings us to the most important point. In physics, elasticity is not about how much something can stretch. No, it's about how strongly it resists being changed in the first place and how perfectly it snaps back to its original form. The key word here, the one to remember, is resistance. The source material just sums this up perfectly with this quote: "A material which stretches to a lesser extent for a given load is considered to be more elastic." Just think about that for a second. It's way, way harder to bend a steel spoon than it is to stretch a rubber band, right? That means steel is showing a much, much stronger resistance to being deformed. To really get a feel for this, let's do something fun. Let's zoom way, way in and see what's happening at the microscopic level. Physicists use this brilliant little analogy for this. Just picture the atoms inside any solid thing, like our spoon, as a bunch of tiny little balls. And all of these balls are connected to each other by invisible springs. These springs, well, they're really the forces between atoms that hold the whole thing together. So these atoms, they like to be a certain distance apart from each other. That's their happy place, their stable equilibrium state. Now, if you try to squish the solid, you're compressing all those little atomic springs, and they push back. If you try to pull the solid apart, you're stretching the springs, and they pull back. That push and pull from those tiny springs, that is the restoring force we were just talking about. Okay, so that's the idea. Now let's see how we can actually measure this stuff and get some hard evidence to prove our crazy claim about steel. So, to compare different materials fairly, scientists came up with the idea of stress. It's basically a standard way to measure that deforming force. Instead of just saying, "I pulled on it," stress tells us exactly how much force was applied over a specific area. It's our input force. And if stress is the input, well, strain is the result. Strain is the measurement of how much the object actually changed its shape compared to how big it was to begin with. It's basically the percentage of stretch or squish. So here's the absolute key to everything. A really, truly elastic material is one where you can apply a huge amount of stress, a ton of force, but you only get a tiny, tiny amount of strain in return. It just strongly resists being deformed. And this brilliant relationship, this ratio of stress to strain, actually has a name. It's called the modulus of elasticity. It's just a number that tells you how elastic a material is. And the rule is super simple. The higher the modulus number, the more elastic the material is. Period. And here it is. The proof is in the numbers. Just look at this table. The Young's modulus for steel is a whopping 200 gigapascals. Now compare that to everything else. Rubber's modulus is so much lower that it's often measured in megapascals, which is 1,000 times smaller.
Steel needs a mind-boggling amount of stress to produce even a little bit of strain. It resists changing its shape like an absolute champion.
Okay, so we've solved the paradox. Steel is more elastic than rubber. But so what? Why does any of this actually matter outside of a physics classroom?
Well, it matters because our entire modern world is built on it. When engineers are designing things like bridges, skyscrapers, airplanes, you name it, they absolutely need materials that can handle enormous forces, huge amounts of stress without bending or breaking. They need things with extremely high elasticity.
I mean, just take a look at a steel I-beam. That shape is no accident. It's an absolute masterpiece of engineering, specifically designed to be as stiff as possible and resist bending. And the whole design only works because it's made from steel, a material that is determined to hold its shape, a material with a super high modulus of elasticity. So the big takeaway here is this. We depend on elasticity not for its stretchiness, but for its strength and its reliability. We build our world with materials that can take incredible loads and snap right back to their original shape, day in and day out, making sure that our buildings and our machines are safe and sound.
And that about wraps it up. Now that you know the real secret of elasticity, I want you to just take a look around you. From the frame of your bike to the tiny springs in a pen, what other things in your world rely on this hidden, powerful resistance to change? Thanks for tuning in.